In this video, we're asked to use a computer algebra system to compute the shaded region between these two curves, f of x and g of x. And there's a couple issues going on that force us to use technology to deal with this problem. First of all, the intersections of these curves have no analytical solution. We need decimal approximations. So I just labeled those intersections as x1 and x2. And the reason we need those is because the function that's on top changes when the curves intersect. So to define the height of a rectangular area contribution, I need to flip the order of the two functions when I cross the intersection. So we're asked first to compute the limits of integration on each region to 3 decimal places. So after I do that, I'll get into visualizing the area elements and setting up the integrals. I may as well label which function is which real quick. If I look at f of x, f of 0 is 1, and I can see it must be this one. And just to make extra sure, when I look at g of x, g of 0 is 0, so I see that this one is g of x. Okay, intersections will occur when I have the same y value for the same value of x. In other words, when f of x is equal to g of x for some value of x. Another way of saying it is we're trying to solve this equation. And unfortunately, that equation has no analytical solutions, so we're going to have to use technology to get this done. I'm going to use the computer algebra system wxMaxima, and you can't just tell Maxima to find the intersection of two curves, but what it can do is find a root of a function. In other words, it can find a numerical approximation of the value of x that makes a function equal to 0. So we need to rephrase this problem like this. I move everything to one side. So if all of this stuff is equal to 0, that's totally equivalent to this equation being true, and that will give us the x's for the intersection points of the two curves. One last thing I'll need before I bounce to Maxima is I need an approximation of the interval in which each of these roots occurs. So one of them looks like it's happening between 1/2 and 1, and the other one looks like it's happening between 1 and 1.5. So here we are in Maxima, and I've written find root, and then I put in this function that I'm trying to find out where it's equal to 0. Notice here that %e is the special name for e in Maxima. And I want to find a root x where x is between 1/2 and 1, and that should give us x1 from our diagram. I hit shift enter now, and I find a root at 0.582 if I round to the thousandths place. Our second root occurred somewhere between 1 and 1.5, and so I just have to change the numbers here. And I hit shift enter, and I get 1.088 for this one. Next, we're going to visualize the area elements for each of these regions. And the idea is that we're breaking this up into rectangles that are so tiny that I get an arbitrarily nice approximation of the area. We're going to say the width of each of these rectangles is a little dx. And then I need an expression for the height of each of these things. And the issue that required us to split the integration interval is that the height has to be a positive number. For dA1, I have the yellow curve f of x above the red curve g of x, and so my height better be written as f of x minus g of x. For dA2, the order is reversed and g of x is on top. If I'm going to get a positive height, I need to put g of x first. All right, then to get the total area, we're just going to add up all of these area increments. So A1 is the sum of all of the contributions to A1, that's dA1. And that's the integral of f of x minus g of x. That's the height of the rectangle, multiplied by the width of the rectangle, dx. Plugging in my functions, I have my integrand worked out, and then I need to put the lower and upper bounds for x in here. Again, I have a decimal approximation for that upper bound. So there is no exact form solution to this integral, and we wouldn't care if there was anyway, because we already had to use a decimal approximation for the interval. So I'm in Maxima, and I'm using the quad QAG function. This is the numerical integration function in Maxima. And you should recognize our function as the first argument here. And then I put in x to tell Maxima what to integrate with respect to. And then I put in the lower and upper bounds for x. The final thing I put in here is just a choice of numerical integration algorithm. And any number from 1 through 6 will do for our purposes. I hit shift enter. Whoops, I forgot a multiply sign between the 2 and x there. That's what it'll do to you. All right, now I'll hit shift enter. And the first number that pops out is the decimal approximation for the integrals. So we're going to keep to the thousandths place 0.265. Next, we compute A2, and that's the sum of all the contributions to A2, the dA2s. And dA2 is going to be a height of g of x minus f of x and a width of dx. And the lower bound on that is x1, this approximated intersection of 0.582, and the upper bound is 1.088. I plug in my functions, negative x cubed plus 2x minus f of x, which was e to the negative 0.1 x squared. And I want to point out here that we can save some time by realizing that this integrand is just the negative of the one before. So I can just put a minus sign in front of the percent e and change the minus on this second part to a plus, and we've got the correct integrand out of this. I can even keep that 0.582 and change it to my lower bound, and then my upper bound is 1.088, comma, and I hit shift enter, and we get 0.052 for this. Finally, we get the total area, and that's A1 plus A2, and we get an approximation of 0.317. The last thing I'd like to point out here is you should always check for the reasonableness of your answer. So we got 0.317 units, and I can see in my graph I have the actual grid labeled where there's a 1 for y there and a 1 for x there. So this big square has an area of 1. Does it look like our total area is about 1/3 of that big square? Yeah, it's plausible, so our answer is at least reasonable. If you find the math content on Zach's Lab helpful, click on the Zach's Lab logo on the right to browse playlists and subscribe to the channel. I produce dozens of new videos per month, and subscribing is the easiest way to find new content. Thanks for watching.